This presentation is about analysis-runtime co-design for adaptive mixed criticality scheduling. This research was undertaken by Ian Bate, Alan Burns, and myself, Robert Davis, who all work in the Real-Time Systems Research Group at the University of York in the UK. The focus of this research is on runtime scheduling protocols and their schedulability analysis. The traditional approach taken is that the runtime protocol is designed first. Typically, this is done without considering the difficulties involved in providing the analysis for it. Schedulability analysis comes later, often in the form of a simple tractable test that is sufficient but not exact. Subsequent work then tends to focus on ever more precise analysis, trading off complexity for greater precision. Finally, exact analysis, if it can be developed at all, is often intractable and may also be quite difficult to understand. It's interesting to look at this from an industry perspective. Industry has a strong preference for simple solutions, so the simple analysis may well be good enough for industrial use. And the marginal gains of more complex analysis may not be worthwhile, given that it's usually much harder to understand and to build upon. The mantra from industry is, don't let the perfect be the enemy of the good. This is often attributed to Voltaire, but is more likely attributable to Montesquieu, who said, le mieux est le mortel ennemi du bien, or the better is the mortal enemy of the good. So, what is analysis runtime co-design all about? Well, the basic idea is to retain the simple analysis along with the schedulability guarantees that it provides, and instead to refine the runtime protocol so that it has improved performance with respect to other important metrics, while still complying with the assumptions of the analysis. In this research, we've applied the ideas of analysis runtime co-design to mixed criticality systems. The system model used is one of dual criticality. Tasks are characterized by their criticality level, either high or low. Low criticality tasks have a single low criticality estimate of their worst case execution time, denoted by C low. High criticality tasks have an additional high criticality estimate of their worst case execution time, denoted by C high. These dual criticality systems have two levels of timing assurance. Requirement R1 for normal behavior, which applies to all tasks, says that if all jobs of the task comply with their low criticality worst case execution time estimates, C low, then all jobs must be guaranteed to meet their deadlines. Requirement R2 describes abnormal behavior and applies really only to high criticality tasks. It states that if a job of a high criticality task executes for its low criticality worst case execution time estimate C low without completing, then only jobs of high criticality tasks are required to meet their deadlines. Perhaps the most popular scheduling scheme for mixed criticality systems is adaptive mixed criticality. The runtime protocol for AMC is based on fixed priority preemptive scheduling. The system starts in normal mode, where all tasks can release jobs. If a high criticality job executes for its C low without completing, then the system enters degraded mode. In degraded mode, high criticality tasks can release new jobs, whereas new jobs of low criticality tasks are abandoned and do not execute. On an idle instant, the system returns to normal mode. Schedulability analysis of AMC makes use of a key concept that's used in the analysis of all fixed priority preemptive scheduling. That's the idea of priority level I busy period. This is a contiguous interval of time during which jobs of tasks of priority I or higher execute. It starts at a time when a job of a task of priority I or higher is released, and there are no other jobs of tasks of priority I or higher that currently have any execution pending. And then it ends at the earliest time after its start, when there are no jobs of tasks of priority I or higher that have execution remaining that were released strictly before that end time. And one of the most useful properties of priority level I busy periods is that the longest priority level I busy period upper bounds the worst case response time of the task at priority I. This concept of a priority level I busy period is used in the analysis for AMC, in particular the AMC-RTB test. This test is in two parts. The first part covers normal behaviour and the second part abnormal behaviour. So the first equation on this slide is a recurrence relation which computes the longest possible priority level I busy period on the assumption that jobs of all of the tasks execute at most for their C low values. The length of this busy period upper bounds the low criticality response time of task I. The second equation for abnormal behaviour does something very similar, upper bounding the high criticality response time of a high criticality task I. However, in this case, the equation makes a number of different assumptions. Firstly, all interfering jobs of high priority, high criticality tasks can execute for their C high values, and jobs of higher priority low criticality tasks that are released by R low as measured from the start of the busy period can cause interference. Now we note that this may be pessimistic because once a single high criticality job executes for its C low without completing, then no more jobs of low criticality tasks can be released. Nevertheless, AMC-RTB is the de facto standard test for AMC. It was first published in the Real-Time Systems Symposium 2011 and has been built upon by many subsequent papers which extend the original work. The performance of the AMC-RTB test is close to that of more complex tests such as AMC Max. AMC-RTB is, however, more suitable for industrial use due to its simplicity and effectiveness. And here, studies into the use of AMC based on this test have been done by a major aerospace company, Rolls-Royce Control Systems, on a full authority digital engine controller or FADEC. It's interesting to consider what we can do to improve upon the AMC runtime protocol. The aim here will be to reduce the time spent in degraded mode. We can do this by reducing how often degraded mode is entered, by waiting longer before entering degraded mode in the first place, and by exiting degraded mode quicker. All of these things are aimed at achieving the main goal, which is to abandon far fewer low criticality jobs. So looking at the diagram on the slide, we can see that with the original AMC runtime protocol, degraded mode extends for the entirety of what we would refer to conceptually as abnormal mode. What we'd like to do with the modified AMC runtime protocol is delay entry to degraded mode and have an earlier exit from it. Notice the difference here between abnormal mode, which indicates when different requirements apply, and degraded mode, which indicates a runtime behavior. So how can we improve upon the original AMC runtime protocol? Well, the idea is to modify the runtime protocol to closely follow the analysis. So we can allow jobs of high criticality tasks to execute for their C high, and also permit low criticality tasks to release jobs until some job of high criticality task reaches a time R low since the start of the priority level I busy period in which it was released. So these things are allowed by the AMC RTB test. The key point here is that we trigger on response times rather than execution times. So to summarize the modified runtime protocol, the system starts in normal mode, where all tasks can release jobs. Then, if an active job of a high criticality task tau I, reaches a time equal to its low criticality response time after the start of the priority level I busy period in which it was released, then the system enters degraded mode, where only high criticality tasks can release jobs. Then when a job of some high criticality task tau j completes, and there's no active job of any other high criticality task tau k that has reached a time equal to its low criticality response time after the start of its priority level k busy period in which it was released, then the system returns to normal mode. And there's a proof in the paper that the AMC-RTB test holds for this modified AMC runtime protocol. The pros and cons of the modified runtime protocol are as follows. The advantages are that it's compatible with the AMC-RTB schedulability test and so retains all of its guarantees. For any given scenario, entry into degraded mode cannot be earlier with the modified protocol, since R low is the latest that this transition could occur when triggering the change to degraded mode based on execution times, as the original protocol does. Typically, entry into degraded mode is much later and is often not required at all. Further, exit from degraded mode is typically much earlier than waiting for an idle instant. The modified runtime protocol automatically takes advantage of any gain time produced when interfering jobs execute for less than their worst case execution time. It also automatically takes advantage of non-worst case patterns of job arrivals from higher priority tasks, for example sporadic behaviours and periodic releases that are not synchronized, in other words don't form a critical instant. The disadvantages are that exact schedulability for the modified runtime protocol is dominated by, in other words it's worse than that for the original AMC runtime protocol. And also it's not compatible with the improved but still sufficient AMC max schedulability test. However, neither of these disadvantages matter if we're using the AMC RTB test. There are three further enhancements to the AMC scheduling schemes that we explored. The first makes use of static slack. Here we increase the C-low values as far as possible for each high criticality task. This delays entry into degraded mode for the original runtime protocol and also for the modified runtime protocol via increased low criticality response time values. We also looked at gain time. Gain time occurs when a job executes for less than its execution time budget. Explicitly accounting for gain time and transferring it to the next lower priority task can improve the performance of the original runtime protocol. However, gain time is automatically taken care of by the modified protocol since it triggers on response times. Finally, we looked at lazy execution. This provides a last chance opportunity for low criticality jobs that would otherwise be abandoned in degraded mode to run via a separate background priority queue. However, lazy execution is not appropriate for all systems as it can increase blocking effects and impacts mutual exclusion primitives that are based on priorities. The performance of the modified AMC runtime protocol was assessed using scenario-based evaluation. The configuration used involved generating 500 synthetic task sets with utilization 0.8 that were schedulable according to the AMC-RTB test, but not schedulable under fixed priority preemptive scheduling as a single criticality system. The task periods used were either semi-harmonic, typical of automotive and avionics systems, or non-harmonic. We set the value of C high to double that of C low for all of the tasks. At runtime, jobs had variable execution times with a probability of exceeding C low of 0.01%. In other words, approximately 1 in 10,000 jobs of high criticality tasks exceeded their C low values. The simulation run for each task set was 10 to the 13 time units, which was enough for at least 1 million periods of the longest task. There were 4 performance metrics that we looked at. The most important was the number of high criticality task deadline misses. In fact, this was always 0 as expected, so is not shown on the graphs. The other three metrics were the number of times degraded mode was entered, the total time spent in degraded mode, and the number of low criticality jobs that were either not executed or missed their deadlines. We explored the performance of different families of scheduling schemes. AMC-RA used the modified runtime protocol with exit from degraded mode on an idle instant. AMC-RH also used the modified runtime protocol, but with the fast exit from degraded mode that I described earlier. AMC Plus used the original runtime protocol with exit from degraded mode on an idle instant. And BP, the bailout protocol, was based on AMC Plus, but with a faster return to normal mode. We also looked at variants of all of these schemes that made use of various optimizations based on static slack, game time, and lazy execution. The presentation of the results involves graphs that are referred to as box and whisker plots. The box is the range of values between the lower and upper quartile of the results, in other words, between the 25 and the 75 percentiles. The line across the middle of this box is at the median, the 50 percentile, and the whiskers represent the 5 and 95 percentiles of the results. The first set of results that we show indicate the number of times that degraded mode was entered. Actually, this is given as a percentage of the maximum number of times that this could happen, which is equal to the number of job releases of high criticality tasks. So here we're most interested in comparing the original AMC Plus scheme with the modified AMC runtime protocol. And we can see here that the number of times degraded mode is entered is reduced to 16.8 and 19.9% respectively of the mean values for the original protocol. In the second pair of graphs, we show the total time in degraded mode as a proportion of the total simulation time. Here we can see that the total time in degraded mode is reduced to 1.7% and 4.1% respectively of the mean values for the original AMC runtime protocol. Finally, this third pair of graphs shows the number of low criticality jobs either not executed or missing their deadlines as a proportion of the total number of low criticality jobs. Again, the modified runtime protocol has a large advantage over the original. Specifically, the number of low criticality jobs not executed or missing their deadlines is reduced to just 2.5% and 8.7% respectively of the mean values for the original protocol. I'd now like to say something about the implementation of the modified AMC runtime protocol. This requires that the RTAS track busy period start times and response time expiries. Firstly, we need the start time of each currently active priority level I busy period for all priority levels corresponding to high criticality tasks. And we can track these start times via order 1 operations at each job release. So when a new job of a task, tau I, is inserted into the run queue, then if it's inserted at the head of the run queue, its busy period start time is simply set to the current time, in other words, the release time of that job. Otherwise, the busy period start time is inherited from that of the task that is immediately ahead of task tau I in the run queue, in other words, the next higher priority active task. To track response time expiries requires monitoring of the response time expiry for all active jobs of high criticality tasks. This is actually very similar to monitoring deadline expiry and can be integrated with it. It can be implemented using a single timer interrupt and an expiry queue. This requires order log-n operations at each job release for queue insertion, and order 1 operations to handle response time expiry, for example, to switch to degraded mode, and order 1 operations at job completion, for example, to switch back to normal mode. To conclude, the modified AMC runtime protocol retains the schedulability guarantees afforded by the AMC RTB test. So, for systems passing the AMC RTB test, all tasks meet their deadlines according to the requirements R1 and R2 placed on mixed criticality systems. The modified AMC runtime protocol provides substantial improvements in runtime metrics compared with the original protocol. In our experiments, it reduces the number of times that degraded mode is entered by a factor of 5 to 6 compared with the original protocol. It reduces the total time spent in degraded mode by a factor of 24 to 60 and reduces the number of low criticality jobs that are abandoned or miss their deadlines by a factor of 11 to 40. The larger of these improvements were observed with semi-harmonic periods typical of automotive and avionics systems. The modified runtime protocol also automatically benefits from gain time and non-worst case job release patterns. The modified AMC runtime protocol is suitable for use by industry. It's based on the simple yet effective AMC RTB test and inherits its guarantees. It has substantial improvements in runtime performance, specifically a large reduction in the number of abandoned low criticality jobs compared with the original protocol. And it has similar implementation overheads and complexity to policing task deadlines. And finally, we'd like to encourage other researchers to explore the idea of analysis runtime co-design. We're aware that significant research effort typically goes into deriving improved schedulability tests that often only realise marginal gains. So let's not forget that other aspects are also important to industry. It can be worthwhile using simple analysis and improving the runtime protocol instead. That brings me to the end of this presentation. If you're watching this live, then now's the time to ask questions. If not, then you can always send your questions to the email address shown on the slide. Thank you.